Hello everybody, my name is Micha Schuster. I'm from the Technical University of Dresden and I will share with you our results on aerial screwing with a fully actuated aerial manipulator. The topic of this paper is in the aerial manipulation research field, a field that attracts a lot of attention in the aerial robotics community. It focuses on developing aerial robots to perform contact tasks in areas that are hard to reach or risky to access for human workers. Aerial screwing itself is a multifaceted and challenging subtask of it, which makes it a good training field to extend the capabilities of aerial manipulators. In our approach, we use a fully actuated UAV that allows for a direct 6 degree of freedom pose control and independent 6 degree of freedom wrench generation. This allows us to use a lightweight manipulator with a low degree of freedom, since the UAV itself already provides the necessary maneuverability. Let's now take a closer look at the task of aerial screwing and its specifications. As we do not focus on aerial drilling, we start at the point where we have a pre-drilled hole whose location we roughly know within an area of several centimeters. Before we can start screwing, we need to insert the screw tip into the hole. When doing this in a position-controlled manner, we would need a positioning accuracy of about 1 millimeter. During the screwing operation, we face mechanical constraints between the screw and the hole, which reduce the degree of freedom to our system. And at the same time, we need to ensure a perpendicular alignment of the manipulator while screwing to avoid jamming. And last but not least, we want the screwing process to be executed without the need of a well-trained pilot giving the right commands at the right time. So how can we solve this task? How would a human craftsman do it? And as we do not have any vision sensors on our UAV, and localizing the hole with an accuracy of 1 millimeter would be very hard anyway. Hence, we approach the task as if we had no close vision of what is happening, similar to a blindfolded human. A human in this case would use his hands to scan the surface and find the hole in a tactile manner. Insert the screw and use the haptic feedback from the screwdriver to align it properly and ensure a good process quality. This is exactly the approach we replicate on our drone. We search for the hole in a tactile way and use the estimated external loads to ensure a proper alignment of the UAV and the screw. And finally, we automate the process that we do not need any inputs from a pilot during operation. Let's now have a look at the system architecture we use to achieve all this. The first modules to focus on are the admittance filter and force controller, which enable the necessary physical interaction control. Second, we will take a look at the state machine and detection module to automate the whole process. The core of the physical interaction control is the admittance filter with its 2 extensions by the force controller and wrench coupling term. In general, the admittance filter with its filter dynamics adapts the desired pose, which is passed on to the controller, depending on the estimated external loads. It ensures a mechanically compliant behavior of the UAV, controls the desired contact force with the PID controller, and realizes the alignment with the screw by adapting the desired position based on the external torques resulting from the mechanical constraints. To automate the screwing process, we use a state machine, which is shown here. When contact between the screw tip and the target surface has been detected, the UAV moves along a star-shaped search pattern to cover an area around the initial search position. After the insertion into the hole has been detected, the detection result is verified by trying to move the screw tip in all lateral directions. If the test returns positive, the screwing process is started and automatically stopped when the screw is fully inserted and tightened. And to retreat from the screw, a detaching force is applied and the UAV enters free flight again. The flight mode detection is able to detect 2 different situations. First, it uses the TCP normal position, its position error, and the estimated contact force to determine the confidence of being in contact with the surface. Second, it determines from the lateral motion of the TCP and the immersion depth into the hole if the screw tip has been inserted. And at the end of the presentation, let's look at the experimental setup and results. On the UAV, we can see a tracker to measure the absolute pose and the plastic screw at the tip of the manipulator. And at the target surface, we can see the threaded hole and a force sensor for ground truth measurements. On the right-hand side, we can see the position of the screw tip with the desired values as dashed lines and the force and torque acting on the UAV. Let's take a closer look at the results. The colored areas indicate the different states of the state machine, and the vertical lines indicate the important events during flight. In the top plot, we see the beginning, the search pattern as dashed lines and the immersion of the screw tip into the hole in the second half of the flight. In the middle plot, the blue and green lines show how the UAV maintains the desired contact force during screwing. And in the bottom plot in the blue line, we see the tightening torque of the screw at the end of the screwing process. And now let's sum up the most important points. We performed the screwing task with no prior knowledge of the exact hole location and without any pilot commands during the operation. The detection algorithm to automate the process relies on the estimation of the external forces and the pose of the UAV. The full pipeline has been validated in the 35 indoor flights with an overall success rate of 86% and a median hole search duration of 9 seconds, as you can see in the figure on the right. And in the future, we intend to increase the robustness of the system and modify the setup to get closer to real-world applications. I thank you very much for your attention.